Draw this in a little picture. We might say that this is our input voltage. Looks kind of like that. Why does it look like that? Our input voltage is a changing function in time. This is AC voltage. So our voltage changes back and forth. That makes some sense. And the output is much larger voltage. Obviously I can't draw it to scale, but there you go. That's the idea. So my point here is that you start with alternating voltage going in and going out. You still get alternating voltage, you just get bigger, or in this case bigger anyway. Does that make some sense? All right. Why are we interested in getting 110,000 volts? Like to get rid of our friends? Just zap. What do you do with 110,000 volts?
You need a lot of volts for X-ray.
You need a lot of volts for an X-ray, yes. We need the volts. We're going to attach it to an X-ray tube. That's the whole idea. And our simplified X-ray tube consists of cathode. And the other end of it is called the anode. And we're going to draw the filament like so. Filament is going to be our source of electrons. And what we're hoping to do is put this high voltage (110,000 volts) between the cathode and the anode. That's what we're wanting that 110,000 volts for. Or maybe we only need 70,000 volts or whatever, but. And then what's going to happen when those electrodes come, the electrons come flying, come off the filament? What happens?
They smash into the anode?
They smash into the anode. Well put. So graphic. They smash into the anode. Big old splot there, right? And when they smash into the anode, off comes a photon. So that's what we want. An X-ray photon, more specifically. All right. If I want to move electrons from the cathode to the anode, what do I need in terms of potential voltage? How is the potential to be arranged? If I want to accelerate an electron, they move towards what?
They move from the negative side, which is the cathode, to the anode.
And what makes them move?
The current voltage.
Not the current. The voltage.
Yep.
The voltage between the cathode and the anode. And so in order to make this happen, this has to be very positive, and this side is very negative. So this will always be our high voltage, and this will be our low voltage. And electrons move from low voltage to high voltage. And if that happens, then all is good. That's how we're going to accelerate our electrons. We're going to put the high voltage on the anode side, the low voltage on the cathode side, and then the electrons are going to go screaming across there and smash into the anode.
So if we were going to say the circuit in this whole cycle, in this whole system, how is it going the circuit?
The circuit?
Or it's alternating?
What is? Well, this is what we need. So hang on. This is. I'm just trying to draw the picture of what we need. We need to have high voltage here, low voltage there. And part of our problem is, what's our problem? That this is high voltage. And part of our problem is that we also have this part of the cycle to contend with. And this part of the cycle, the voltage goes the wrong direction. So this would make the anode negative and the cathode positive. So our problem with this picture, this is what we need, this is what we have, and the part of this voltage wave that is bad news is this part. We need to get rid of these because they present a problem. This would cause this part of, if I attach this voltage to here, I'm going to force the electrons back into the cathode. And I don't want that. So what shall we do about that? Any suggestions? Somebody thought of something, you know. You're waiting for me to tell you what it is, right? What is the sort of the simplest thing you can imagine? That's right. Just get rid of it. So this is now our high voltage.
So we want to get rid of our opposite low voltage, right?
Well, we want to get rid of the negative half. And this is our low voltage. 0 is our low voltage, and then we have high voltage at the peaks. And since we just chopped it off, we got rid of it, we don't have any negative voltages. And that's what we want, no negative voltage. And all is good, or pretty good anyway. This gets a name. It's a rather odd name. Half wave rectified. The half wave is obvious because we threw away half of the wave. But rectified, I mean, that's something out of the 19th century. Rectified is if there was a problem. They fixed the problem. They rectified it. What was the problem? The negative voltage. All they did is get rid of it. Then a little bit later on, somebody figured out, but wait, we don't want to just throw away that other stuff. With a little bit of engineering, they could flip it over. So now we have full wave rectified. This is voltage and this is time. So we've fixed our waveform with something called a rectifier. So what are we doing with this voltage waveform? Yes?
I'm sorry, I'm just a little bit confused on the full wave. So are the ones from the bottom flipped over to the top or something?
Exactly.
Oh,
Yes.
Sounds like alchemy.
Sounds like alchemy, huh? It's just a little bit of electronics. It's not terribly complicated. As far as electronics go, it's relatively easy to do. But what we need to do, more than understanding the electronics, is to understand how that picture impacts the electrons traveling from the cathode to the anode.
When we switch it to full wave rectifier?
Well, both of them, half wave or. How does this impact the electrons traveling from the cathode to the anode? Let's start with the half wave. So first of all, on the vertical axis, what do we have? Voltage. And high voltage means a lot of acceleration for the electrons. Low voltage means little or no acceleration for the electrons. So there are moments in time when there's a lot of acceleration, and there's moments in time when there's no acceleration. So you see those times.
It's not consistent.
It's not constant.
Consistent.
Constant or consistent?
Consistent.
It's very consistent, it's just not constant.
Um,
I mean, it's very regular, it just does that forever. It does it all, it'll do it all day long. But it is not constant at high voltage is the important thing. So that is a really important feature that the acceleration, and this is of the electrons, is not very constant. There are like momentary times when it's really big and we get our 110,000 kilovolt, 110,000 volt electron, and then we have to wait. We gotta wait for this time where we don't have any electrons whatsoever. And if we're waiting for each electron to get to the anode to make a photon to produce our image, what this does is extends the exposure time because you're getting fewer electrons on target per second. So with this, you can cut your exposure time in half because you're using every pulse. So that's the first advantage of that is the advantage of full wave rectified over half wave rectified. Just cut your exposure time in half. All right, on these diagrams, show me where you get high energy electrons. At the top. Yes. All right, these are our high energy electrons. If those areas produce high energy electrons, what do the other areas produce? Low energy electrons. So all of this is low energy electrons. So you see that this waveform, this voltage waveform that you had very little interest in until now, produces both high energy electrons and low energy electrons. High energy electrons are going to produce high energy photons. What are low energy electrons going to do? Low energy photons. Very good. Monty Python teaches physics. All right. Problems with low energy electrons and low energy photons.
More scattered electrons.
More scattered.
Most scatter radiation.
More
Yeah,
scattered.
radiation.
Scattered radiation is different than scattered electrons.
Okay.
Scattered photons. Yes, you would get more photon scattering, which is something we have to talk about later on. You also increase patient dose. You get more fog. The patient gets more dose. And so it's a lot of no good. So our goal is to eliminate the low energy photons. To do that, we have to eliminate the low energy electrons. And both of these have lots of low energy electrons. And that's the major problem with these two simple solutions, is that they have lots of low energy electrons.
So now I have to deal with the current to give them the punch.
Hang on. There's a really strange word. It's called voltage ripple. All right, and both of these waveforms have 100% voltage ripple. So what, considering that they both have 100% voltage ripple, what do you think voltage ripple means?
They both have
Changing
them.
strength of electrons.
The changing strength. Right.
Can you hold this?
How do you see the 100% on that graph?
They're all positive.
They're all positive.
So
The rectifier took care of that. But the voltage that's applied to the electrons goes from a low of 0 up to my maximum voltage. So that's just saying that the voltage going between the cathode and anode varies between 0 volts and 100 volts, 100%, the full voltage. So when I'm applying 0 volts to the cathode, the electrons are not being accelerated. In this case, it's not for a very long time, but it does happen. And then at some point, the voltage increases from 0 all the way up to its maximum value. Hence, 100% voltage ripple. It's important that you see this voltage ripple now, because it's going to get more confusing in just a minute. This one also has 100% voltage ripple because the voltage literally goes from 0 up to the same peak, right? That's why they have the same 100% ripple. This one has big time gaps between them, and this one has small time gaps. That doesn't have anything to do with voltage ripple. Voltage ripple is the distance from the lowest voltage up to the highest voltage. All right, so now that you have some idea of what voltage ripple is, the next incarnation of this version of this thing is to, well, we'll take full wave rectified signal here. So far, that's just the same as what we had before. Some enterprising engineer said, well, what I'm going to do is take 3 of these things and I'm going to superimpose 3 of these, but I'm going to stagger them slightly. So this engineer said, I'm going to put another one here. And a third one like so. And the result is the voltage never falls to 0. When I add the 3 of them together, I get something that has a little bit of ripple. Not a very good drawing, but you kind of get the idea. The voltage never goes to 0. So this is full wave Three-phase. Full wave, three-phase. The full wave you kind of get from the previous discussion. The three-phase has to do with the three of these. There's your first one, there's your second one, and there's your third one. That's why there's three phases in there. And you can see that it does make it a little bit smoother, well, considerably smoother. And for this, the voltage ripple is, if memory serves, is on the order of 12%. Don't quote me on the 12%, I'm kind of forgetting that one right now, but I think it's about 12%. But let's just suppose it was 12%.
Sorry, when you say 12%, this 12% of what?
I'm glad you brought that up, glad you asked. If our maximum voltage is 110,000 volts, what is our lowest voltage?
In this case?
In this case, it's not zero, but it's 12% less than the maximum.
Oh, okay.
And how do we calculate 12% less than the max?
96,800.
96,000, that's an answer, that's not how we calculate it.
Take away 12% from the full voltage.
Okay. So 100% minus 12% is also known as 88% of 110,000 volts. And that would get you, what, I didn't bring a calculator, your 96,000? Sounds about right.
96,800.
96 point, what'd you say?
96,800.
96.8, we'll call it kilovolts. So now our lowest energy photon is going to be a 96.8 kilovolt, kilo electron volt photon, which is much higher than zero. So we've eliminated the low energy photons. Still, that's quite a bit of spread, and by lots of other engineering applications of which they work to produce lower forms, they have something like what they call a high frequency generator, which I think is probably used in most of these machines right now. And it produces a ripple of less than, I believe, 1%. So they can get the voltage ripple down very, very low. I mean, ideally, of course, you'd like to have the voltage ripple down to zero, but that's not possible. All right, so we talked about voltage ripple. We talked about the auto transformer.
And you said the last machine was called a high frequency?
This is a high frequency generator.
On those last two examples, so we're seeing the peak is that high, but aren't all those lower wave photons still being emitted as well as the high peak ones? Or?
Good question, yes. Let's talk about the next aspect of the things that we have to look at are the we are now talking, and it's good to get this here, the X-ray spectra. So a type of new way of thinking about this. We have X-ray energy. And we have number. So this is called a histogram. And on the vertical axis, it just counts number of photons. Or on the horizontal axis, it would calculate the photon energy. So let's talk about the ideal case. So we got number, X-ray energy. And let's just suppose we had 110 volts. So this is 110 kilo electron volts for energy. And what we would see in the ideal case is just a big spike of all our photons produced at that energy. But how are those photons? Now we're talking the photons, not the electrons. Where do the photons come from?
The smashing of electrons at the anode.
These photons come from the smashing of the electrons into the anode. Yes, well put. All right, so this is ideal and does not happen. What does happen when we do this little experiment, number, kilo electron volts. Depending on how things go, we tend to get a distribution that looks something like that. So no matter what we do with our, well, we get, well, first of all, what is this graph telling us? This is photons. Tells us we get very few high energy photons no matter what we do. And also tells us we get lots of low energy photons.
Even with the curve rectifier?
Well, now I'm going to draw some different shapes in here. So I'm going to draw a shape that looks like this. And I'm going to draw another shape that looks somewhat like that. And this will be single phase. And the red one is high frequency, which I'll just abbreviate HF. And you see the effect of rectification on the X-ray spectra. So when we have that single phase full wave, remember we had the 100% ripple? So we had a good fraction of time where we were getting low energy electrons. Those low energy electrons produced just an awful lot of low energy photons. When we went to three phase, there was much less. The ripple was didn't go all the way down to zero, which effectively eliminates a lot of the lower energy photons. And the high frequency generator were able to seriously eliminate the low energy photons, which is the major, the fact that we're able to get rid of the low energy photons this way is the major importance of this stuff for you. Because ripple does what? Voltage ripple, what is it and why do we care about it? Think of that as the next question on your next test. Voltage ripple. Explain, why do we care about it? What is it and why do we care?
Ripple.
It affects the quality of the.
Absolutely affects the quality of the X-ray radiograph. And it affects it in a negative way that we want to eliminate ripple as much as possible. So we'll step away from that for a few minutes. I'm doing good. And we're going to talk about, what are we going to talk about? We're going to go back and talk about currents again. Tube current and filament current. In both cases, we're talking about electrons. And the other one, we're talking about the filament current, we're talking about the electrons in the filament itself. So, here's my cathode. If I want to think of the electrons that are moving from the cathode to the anode, that is my tube current. The electrons that are in the filament, something else, are in that thing. So the filament current and the tube current are related to each other. Because the filament current is the current necessary to get the filament hot. When the filament gets hot, electrons jump off the filament. It's called thermionic emission of electrons from the filament. So this filament wire gets very hot, electrons jump off, then the electrons are accelerated and become the tube current. So the filament current and the tube current are related. If the filament current goes to zero, what happens to the tube current?
Zero.
It'd have to be zero, right? All right. So I'm going to draw a graph with two axes, IF, filament current, IT. Actually, I want to switch the order of those, I'm pretty sure. Good number here. We're going to put the tube current here and the filament current here. And this is gonna be 0, and this is gonna be something like 5 amps. And this is going to be 0 there, and this is going to be something like 200 milliamps. So our tube current relative to our filament current is gonna be quite small. And of course it starts at 0, because if one is 0, the other has to be 0. But they go up in very complicated ways. And these different graphs correspond to different voltages. But the general features are, the more you crank up the filament current, the more the tube current increases. That should seem obvious, yes?
Okay.
What I'm trying to illustrate here is that there is no nice relationship between this. Very complex relationship between them. So there's no formula. All you get is a graph. And you know that it has some kind of, yes, it starts at 0 and it goes up and it increases, and it depends on which KVP you're using, the relationship between them. So it's just a graph you would look at. And there is a graph in the book, which I'm trying to recall. If I have a picture of it handy someplace. That'd take too long. While we're waiting for Firefox then, we'll draw another graph. This time of KVP. And this is tube current. So this is going to be 0, and this will be up around 100 kVp. Oh, by the way, the use of the P there and the VP, what does that P stand for?
Peak.
Peak. And what peaks are we talking about? The voltage peak. Yeah, that P is for the voltage peak. And as you've seen in these spectra, what we're talking about, of course, is the peak voltage here, not the voltage at other times. We're only interested in the peak voltage. That's why we're interested in the peak voltage. These things do a complicated sort of thing that looks like so. Let's just say that this is this is perhaps the more interesting graph. It shows the tube current, how the tube current changes. Remember the tube current, the tube current is going to be related to your exposure time. If you want to reduce exposure time, you have to increase the tube current. If you want to increase the tube current, how can you increase the tube current? What can you do to boost a tube current and make it bigger?
Lower the voltage.
What can you do to make a tube current bigger? Well, let's take a look at this graph first of all. What can you do to make a tube current bigger?
Increase the amps.
You can increase the filament current. If you happen to be, say, down here and you want to increase the tube current, what can you do?
Increase KVP.
Increase the KVP.
Okay.
So if you're in this region, you can get there by two ways. You can increase the filament current. That takes you up to the second line. And you could, or you could just increase the KVP. That would take you up here. So you have two ways of increasing your tube current. Why do you want to increase the tube current? You want to decrease the exposure time.
Okay.
All right. Now you're sitting here and you want to increase the tube current. This is a little bit different. What happens if you increase the KVP?
Levels off.
Levels off. Increasing the KVP is not going to increase the tube current. Your only choice at this point to increase the tube current is to increase the filament current. So there's the attention that we have to pay to this graph is that, you know, in this region, we have two ways of increasing the tube current. When we're up in this region, we only have one way to increase the tube current. So we have less flexibility at high KVP.
Why can't we change the, these are both current of the filament, right?
These are filament currents.
Yeah. What? Why
long as
can't we
that's-
just change the bigger one in this case?
You can. Well, I'm just saying you have less flexibility. If you're in the high KVP region, you have less flexibility.
For both.
Well, the only way to increase it is to increase the filament current. But if you're down here, you have two ways to increase it. You can either increase the KVP or you can increase the filament current. So in this region, you have more flexibility. And flexibility is a good thing because you may not want to increase the KVP. You may not want that much penetration. And so now that we kind of understand why we care about those curves, what causes them? And there's some really strange terminology here. So the two regions are broken down into space charge limited and emission limited. We'll see if we can come up with some understanding of what those two regions correspond to. Emission limited is perhaps the easiest one to understand. Because at high KVP, this is the potential between the cathode and the anode. High KVP corresponds to what physical attribute of what's happening to the electrons?
Penetration.
It also corresponds to penetration, but that would be of the photon. Speaking of just the electron coming from the cathode to the anode, what's different at high KVP versus low KVP? Very basic. Acceleration. Which one has more acceleration?
High KV.
High KVP, yes. So at high KVP, you're thinking the electrons have a whole lot of acceleration. And at low KVP, the electrons do not have a whole lot of acceleration. So the way to think about what's happening here is that the electrons, as soon as they come off of that filament, they're just accelerated and they're out of the way. And what we are limited by is the emission of electrons from the filament. So if we're in the emission limited region, the only way to get more electrons from the filament is to increase the filament current. So that's why I said the emission limited region is more or less easy to understand, because we're limited by the emission of the electrons from the filament. Less electrons being emitted from the filament, the lower your tube current has to be. Conversely, The more electrons you emit from the filament, your tube current goes up.
So is the emission limited area just the area all below that lower line?
It's where this curve flattens out.
Oh, where it flattens.
Yes.
Everything you just said, is that in the book?
Yep.
Okay,
And he's got some great graphs.
because I missed
You missed it.
some part.
Some parts. Let's see, somewhere along the line they had some graphs. I know I copied his graphs. There it is. This is the graph in the book. So we have tube current on this side, and it's going from, we got 0 up to 1200 milliamps. And we've got kVp going from 0 up to 150 kVp. And you see the emission limited region, the space charge limited region. And he's calling these maximum currents the saturation current, which is much more of an engineering terminology than what you're interested in. All you care about is this is where you can't change the tube current by way of increasing kVp. That's all the current you can get out of that kVp, and this is because the electrons are, it's dependent on the electrons being emitted from the filament. So look for that graph in the book, and the other one is right next to it. Looks like I had some questions in mind. Let's see, I'll have to print this out for you. In the following graph, determine the tube current at 75 kVp and a filament of 4.6 amps. And if anyone had the book here today? No, all right. Don't carry around any extra weight you don't need to carry. But I think it's somewhere in chapter 5, it might be in chapter 6, I'm not sure. So a typical example, if you're looking for a tube current of 75, a tube current at 75 kVp. Well, find 75 kVp, and it was 4.6, you read up, you read over, 400 milliamps. Just being able to read that graph, yes? The filament current at 125 kVp and a 200 milliamp current. So, can't get it all on one screen, can I? There we go. All right. 125 kVp, that's halfway to the end here. And we're looking at 200 milliamp filament current, tube current. (125 kVp), read over to 200. And what filament currents could I use?
All three of them had
If it's that low,
It's not there.
Not there. I can't get 200 milliamps at 125 kVp. At 100, the only at 200 milliamps, I'm already down at 25 kVp. I don't know what I had in mind with that question.
To see if they understand, they will tell you we can't get it.
There we go. Yeah, can't be done.
It's a trick question.
Trick question. Okay, a maximum tube current at 4.8 filament current.
600 milliamps.
Easy one, 600 milliamp. Let's try this one. What settings would produce 400 milliamp tube current?
100 milliamp.
What settings could I get to here with? I could get there at about, say,
50 kVp.
15.
what, about 15 maybe? 15 kVp at a big 5 amp current. I could get there at maybe about 25 kVp with a 4.8 amp current. And I could get there with a 50 kVp at a 4.6 amp current. Okay, so we spent a lot of time talking about emission limited. We have some feeling for emission limited. What does emission refer to?
So using that graph, you always kind of have to, the KVP line is gonna always kind of be up. You can't just kind of go straight up.
The KVP line? Well, if you add 100 KVP, at 4.6 you get 400. At 4.8 you get 600, and at 5 amps you get close to 1,000. It is a complex graph to read. Try this one more time. What does emission refer to?
Electrons coming off the filament.
Electrons coming off the filament. Think of it this way. Emission limited, you are limited by the number of electrons coming off the filament.
We can speed them.
Yeah. Now we come to this other monster, space charge limited. And notice that space charge limited is mostly around the low KVP. Sort of anything below, anything below 50 KVP, but even up at high filament currents, it goes up a bit higher. Space charge limited. It's around low KVP. Sort of a metaphor for space charge limited. You've been in a crowded department store and you've gone up an escalator, but people who have gotten off the escalator at the top have not moved.
Hmm.
You kind of understand what that might feel like? Well, you know, imagine the escalator, there was sort of some weird continuous thing where if you couldn't get off, you just had to keep going. And that's kind of what space charge is. If the electrons that have been emitted have not been accelerated, they build up a cloud of negative charge. They build up a cloud of negative charge around the filament. And that negative charge around the filament prevents other electrons from getting off of the filament. It's space charge reduces the tube current.
Professor,
Yo,
can you repeat that once more? If electrons have...
I'll give it a shot. We'll try. I'm just gonna copy this where I can write it down here. There we go.
They build up.
If they have not
That
been
escalator.
discharged, they become negative?
So it creates this electron cloud that's like this huge
So
negative
here's our
charge.
filament.
It's
Here's our
just exactly
anode.
like that elevator
Hmm.
analogy. That's pretty great actually. But yeah, it's like it just
And
crowds up, and then because of all this negative charge, it can't escape because negative repels negative. So they're just kind of trapped there in their own cloud.
So that is the bunch of electrons that have been emitted, and they hang around this cloud for a bit, or they're not accelerated right away. That's why it happens at low KVP. And there is your space charge, limited domain, and what's causing it.
So is that the darker gray area is all space charge limited?
Yes. Well, no. I forget exactly what he's trying to do with this. He's trying to sort of indicate the space charge limited region is really the lower KVP. There's some effect of it as you go into higher KVP. But in this region, you're definitely, the light gray is definitely all emission limited. And somewhere between here and here, there's kind of a transition between the two. And this transition has finally occurred when you get to this leveling off point, which he calls the saturation point. So at the saturation point, you're definitely reached emission limited. In between, at low, then you're strongly affected by space charge, less so, and finally space charge has no effect. Would be the way to think of that complex diagram.
Prevent other electrons from being emitted.
More about X-ray spectra.
Since the clouds
On
have to
a cloud.
yeah. And they prevent the electricity.
We'll talk a little bit about this because we're going to be dealing with these graphs basically from now until the end. So we might as well start talking about them. One, how is the X-ray energy related to the electron energy? And we did this the first week. But you can't remember anything that happened back there.
Can you repeat the question?
How is the X-ray energy related to the electron energy? Of course, in that first week, I was only wanting you to think about using your calculator with those numbers. But you had that worksheet that had to do with the electron speed and energy and something
V
called a
squared
fraction.
over-
Yeah, there was all of that. How did the X-ray energy relate to the electron energy?
Like directly proportional?
Not
It could
directly
be
proportional.
as high as
No.
the energy level, but the photon is usually going to be smaller.
Yes, the photon energy, EP. EP will be less than or equal to the electron kinetic energy. Second question, second little detail that we want to fill in here. How is the electron energy related to the potential?
So in the first case, EP is the
Photon,
EP is the photon and EK is the
electron kinetic
the
energy.
X-ray energy. No, it's opposite. I don't know. Okay, I have to do that.
So the photon energy is less than or equal to the electron kinetic energy. Photon energy cannot be greater than that. And the second point is, how is the electron kinetic energy related to the cathode anode voltage?
Stronger the differential, the faster the speed.
No, this one is actually easier than that. So the electron kinetic energy is literally just the electron charge times the voltage. And what's the charge of the electron?
1.602.
1.602. But in easier units? So we're going to take the electron charge as E, and we're not going to write it as 1.602 unless we need to. We'll just leave it as E, times our voltage, which happens to be thousands of volts. Move the E between them, and we get our unit of energy. So our unit of energy here. That's our electron charge. And this is our voltage. And it's kind of a simple idea. Our voltage times the charge gives us our energy. It's also a cause of quite a number of mistakes, particularly in the book. Several times he writes something and he's talking about energy and he just writes voltage, or he's talking about voltage and he writes energy. That little E that goes between them causes lots of problems. And of course, we're always talking about the peak voltage, right? So it's KEVP and or the KVP, our peak voltage. So if you have a peak voltage of 110 volts, what's our peak energy?
110.
110 electron volts, kilovolts. Easy enough, just a little something to watch out for. All right, so on this graph here, I'm going to put 110 KEVP. And this refers to my 110 volts, 110 kilovolt setting. So I turn the machine up to 110 kilovolt setting. My maximum energy is 110 KEVP. All right. With the machine at 110 kVp, my maximum electron kinetic energy is going to be, my electron kinetic energy, rather not the maximum, but the electron kinetic energy at this machine setting,
110.
KEVP. Watch out for that E. And if my maximum electron kinetic energy is 110 KEVP, what happens to my photon energy?
It's gonna be lower than or equal to the energy, electron kinetic energy.
Which is why we will generally draw graphs that look like that. So these are the photons produced at this machine setting. So if you set the machine to 110 kVp, you get photons They could have some with that energy, but most of them are gonna have less. Just because of how the photons are produced. And this point, focus on that point and come up with a name for it. An obvious name would be maximum photon energy point.
Sure.
Something simple like that. Something nice and simple, that would have been great. That's not what it ended up with. Ends up getting called the point with the minimum wavelength. And why is that? How is wavelength related to energy?
The bigger the wavelength, the less the energy, right?
Right. That's where our good old friend H comes in. E is equal to HC over lambda, or lambda is HC over E. And we're talking about the photon energy. So number energy. So they make a big deal about how this point here is the minimum wavelength. Lambda minimum is equal to HC over
So basically, the minimum wavelength is the HC over the max photon energy?
Yeah.
Okay.
That's all there is to it. It's not very complex. It's just they throw in this new name, the minimum photon wavelength. Little additional stumbling block. All right, we did a lot today. That's a great place to stop.
Sure, go ahead.